Somebody in the chat put, hello everyone, Bruno here, joining from Uganda.
Wow.
Hello, Bruno.
Welcome, Bruno. Good to have you here. Thank you for joining this morning. And we are going to just get started. Oh, I have Dr. Shigo here as well. Good morning to everybody.
Asia today. Asia today.
I'm going to make some people co-hosts so that Dr. Shigo is going to be a co-host here. I'm going to make our speaker today co-host. And yeah. So, Pablo, I will let you share your screen at some point.
Okay.
Yes.
So
Sorry about that.
I
Yeah.
have the same, I have the same background of my presentation here.
Exactly. Yeah, but I will share my screen first. Let me just work on um okay. Okay, replace current sharing, yes. Um Show this. I think it's this one. Okay. Can everybody see my screen?
Not yet.
Yes, okay.
How about now?
Yes, we can see it.
See your skin, the CONGA mission,
Yes.
agenda September 25.
Yeah, you can see. You can see very well.
Oh, I see it now.
You see now? Or maybe
Yes.
because you were sharing and then share
Yeah,
over it. Okay, that's why.
I can see in a tab upstairs, up in the
Okay,
top.
maybe if you stop sharing, you could.
No, no, yeah, I see it now.
Okay, good. So I think we should just get started and welcome everybody again. It's good to have you for the 13th CONGA meeting. CONGA is continuous network of ground-based instruments over Africa. It used to be ground-based, GNSS receivers, but we are thinking in a broad way now to put other instruments at some point. So we are generalizing to be ground-based instruments so that other things can come in later on. Now, today we are having the privilege to have Dr. Pablo Reyes. Pablo Reyes is an engineer, is my colleague at SRI International. It's very nice to have him here to talk to us about what he's doing on radar. Dr. Ray is in charge of the operation of the AMISRs, all of the radar in the north and some in the mid latitude. He has been working on this for several years, and today he's going to tell us some of the things that we need to know about the radar. And please feel free to ask him questions. And I will come back to introduce him for the lecture, but before he start his talk, let me just tell us that very quickly, this month of March, we have a lot of people joining us on becoming a member of this CONGA. Like we have 15 people. I have listed their names. So if you are here, you want to say hello, please feel free to take the floor. And we have 15, and you can see they are from various institutes, and some of them are from the US. We have two from Uganda, and somebody just said he's from Uganda. Mr. Bruno is from Uganda. Sorry if I mispronounce your name. Maybe it's Dr. Bruno. So we have people from DR Congo, Democratic Republic of Congo. I think that's the first time we're having somebody from there. That's interesting. We have people from Kenya. Oh, we have 3 people from Uganda. Wonderful. So these people are researchers, lecturers, students, as you can see here. That's wonderful to have. And these people, the interesting thing is that most of these people are located in the region we are trying to reach. You see this region here? This is the mission of CONGA to be able to put ground-based receivers or ground-based instruments all over these places. And this is our mission. So when we have people coming from that region, it's a very big privilege to have them because very soon we're going to be contacting you guys when the instrument is ready. Now, I just make this distribution. I try to think about what is the samples of people that we have, the their occupation. You see, we have 33% of, this is just a sample of people joining us this month only. So I collect a sample of that nature. So you can see 33% are students, um, researchers are 27, lecturers are 27. No, okay, that's nice. So, and we also have people joining us from other area like survey, geodesy, or yeah, geodesies. So you can see that it is possible to actually expand the vision and mission of CONGA in such a way that everybody is benefited. And we have people in the countries where they come from. 7% from Ethiopia. I think the highest is from Nigeria. I think that is a very good sample because Nigeria in the past population that I make this plot, Nigeria got like 50 something percent. And we have right now we're having about 20 countries from Africa that are participating on this. So that is very, very good to know. So, and lastly, we have people that are interested or able to host the instrument. So this is also good news. We have people who are interested in hosting or are able to host. Some people are not able to host due to several reasons, but people who are able to host are almost 70%. So that is really good. Um, so I think I will stop here. I don't know how much time our speaker will take today, but Dr. Pablo, let me stop sharing my screen. Dr. Paulo, you have up to 30, 45 minutes. Feel free to take your time. People that are here are students, like we are seeing in the chat. Students are more. We have lecturers from all over the world. We also have researchers. So a lot of people are looking forward to use the radar, particularly the FISA and the AMISRs. So, or the RASA N and RASA C, but they don't know how to go about it, or they don't even know what it is about. So today is a privilege that we have to have someone that has been working on this instrument for a long time to talk to us and introduce us to the instrument in a very unique way. So without any further ado, I will give the ground to Dr. Reyes. Please take the floor.
Thank you, Olu. Thank you for inviting me. It's a privilege to participate here in this 13th CONGA meeting. And so my name is Pablo Reyes, as Olu mentioned, and I've been involved in these atmospheric radars since almost 25 years. These are some of the radars that I put in the background that I've been like present. I've been working on, and I've visited them, and then I started at the Jicamarca Radio Observatory down in the lower left. which is a radar that is located in equatorial regions. It's like something like, and we'll probably see phenomena that will be similar to what a ground instrument, a big radar in the equatorial region in Africa will look into equatorial aeronomy when. So I will, this is my, let's see, how do I advance here? Okay. I will do a very quick outline. It will be just examples of observations with radars, what kind of data we can collect and measure with them, some practical applications of or some derived products from what we can do with radar data, and I'll give you some insights of where to get the data, where how to know if there is available data and how to access it of this incoherent scatter radar, mainly data. So right out the bat, the type of radar that I'm going to talk about is this large, big, powerful transmitters of the order of a megawatt, plus minus. It differs, and then these are this mesh the type of measurements is what I'm putting an example on the right. The incoherent scatter radars are powerful instruments that can resolve a whole column of where it observing. So these plots on the right are altitude or range time intensity plots, where the main parameters that incoherent scatter radars measure is electron density, the temperature of electron and ions, and the bulk movement of the plasma, so up and down along the line of sight below of the radar. In a simple, so and these are the type of radars that current and past ISR facilities. I took this from a website that I will mention later of AMISR manual that one of our colleagues that I see also in the participating here, Leslie Lamarche, put together, and I stole this from there, and I stole other um, uh, some other parts of the presentation also from there. So if the data here that I put an example here is the Resolute Bay is we call it Riser and Resolute Bay Incoherent Scatter Radar North. It's located here there in Canada, northern Canada. In the Poker Flat Incoherent Scatter Radar is located in Alaska, here in northern in USA, northern USA. There is other incoherent scatter radars like the Millstone Hill radar. I will show some data too, or the Jicamarca. This is a equatorial radar here, put there like almost more than 60 years of observations here in Lima, Peru, equatorial regions, the Recibo, and well, many other radars, including dish antennas or phased array like Poker Flat and Jicamarca or Sanya, new radar. And there are other radars I don't see here. The Quadraline, like in the Marshall Islands, is another big radar. Is mainly for surveillance, but big, powerful transmitters and antennas will collect incoherent scatter returns too. Very brief about the main instrument that I work right now at SRI. I've been working at SRI since year 2017, so it's going to be almost 8 years. And so it's a phase array um, that can point a beam to scan the atmosphere it can change the beam location at every pulse. So let's say if we have an interpulse period, so of millisecond, every millisecond, you could like look to a different location, and that way you can cover vast regions of the atmosphere that you are observing, and you can do imaging of that, or you can like derive vectors from the volume that you are observing. And so the uh, Poker Flat is in Alaska, in the Midland here on the map. And there are two radars in Canada called Resolute North, looking north, and Resolute C from University of Calgary that used to be working. Right now it's not, but it looks to the south. And there is data in the database that you can like look at this type of observations. So a radar like this is another type of radar in Millstone Hill in MIT. This is located here, Millstone Hill radar in this location, and but as any other radar, it has a beam. So incoherent scatter radars can measure at every altitude for whenever you are pointing parameters of the ionosphere. So in this case, this is a typical incoherent scatter radar plot. Again, altitude versus time. So a very powerful instrument because it can measure all the time what is happening above where the beam is pointing, right? And it measures it measures the parameters at every height. Of course, as it goes higher in altitude, it it starts losing like power because we are transmitting large amount of power, and then a fraction of that, like re-radiation from the free electrons that are in the ionosphere, will come back, a fraction of that, and will be detected. As you go farther away, it gets more difficult to estimate accurately what the parameters are, because there's the signal that is coming, that start coming back, is like weaker and weaker. So you can see at the top parts of radar data it's the uncertainties are larger, but in the bulk of in the F region, it's like you can see very precise measurements of the plasma parameters. And to obtain those parameters, it relies in of the incoherent scatter theory, which relates the measure spectrum, power spectrum that comes back with roughly, this is a very simplistic way to just see. I obtain a spectrum. I obtain a spectrum by doing what the plasma, the phenomena that's happening in the ionosphere is like a stochastic process. So you have to send a lot of pulses, do a lot of statistics like average, and try to estimate the spectrum. And then based on the shape of the spectrum, you can see things like the ratio of the temperature of electron and ions is related to this valley in this double hump spectrum, or the width, total width of the spectrum is proportional to the temperature of the ions. Each of the species divided by the mass of this of the ions. The total area under this curve that is called the ion line is like proportional to the electron density, and how this whole double hump spectra is shifted up or down of the transmitted frequency is what give us the line of sight velocity that is like here on the bottom part. So the mesh, so those are the main parameters that you can obtain with incoherent scatter theory with these big radars. You see here the electron densities in the order of 10 to the 10 to the 12 in this case. This is the color scale, the temperature of electrons and ions, and the line of sight velocity. So how the whole plasma in the ionosphere is moving up or away or towards the radar. And now, if you so this is at higher altitudes, latitude, sorry, where the radar is pointing. So there is an angle. When you are pointing the radar up, you see magnetic field lines, and you can even point the radar parallel to the magnetic field lines. This is high latitudes. But if you point the radar at equatorial regions, like for instance at Jicamarca, or what would you like at a radar that you will have probably in Central in Africa, where you guys are at that map where all show all the places where you could put these GPS receivers. So that's equatorial regions. And so when you point, you could point your radar perpendicular to the magnetic field lines. And what you will see is some, besides the incoherent scatter radar returns, like it's shown here in these arrows, you also see some coherent echoes. What I mean by that is what is called incoherent scatter. You are like scattering back from a volume filled with electrons and with plasma. So the electrons are getting and they're re-radiating in a sort of incoherent matter. So all this is adding up in the receiver. But the coherent echoes are like sometimes like they are aligned or they are like field aligned, so plasma irregularities, and you get a much stronger return. That's strong that you don't need an super powerful incoherent scatter radar. You can use what is called also like a coherent radar. Like it's like instead of megawatt of power, you can use like 10, 20 kilowatts of power. Coherent scatter radars will scatter back from these irregularities. Some of the known irregularities at equatorial regions is, for instance, the plasma bubbles, also called as spread F. They're called spread F because of they were first described and detected with ionosomes, and you will see instead of having like a nice curve of an ionogram, if you have seen ionograms before, I should have provided one here, an example. But then when this phenomena happened, and of course in the GPS realm also, this causes a lot of scintillations at equatorial regions. And so it's like low density plasma bubbles that are that are going up and creating a lot of structures and things that a radar is very sensitive to, and it's also it totally blocks the incoherent scatter return. So wherever you have these strong returns from a coherent scatter, then you won't be able to measure the plasma parameters, but you will be able to characterize. And there is a lot of studies about spread F, initiation of spread F. It's a phenomenon very common in equatorial regions. Also, also, there is mesospheric perennial mesospheric echoes in the mesosphere around 80, 90 kilometers, and the like almost daily equatorial spread F. It's like a whole current of plasma, like in equatorial regions that can like also produce a lot of coherent scatter, and it's very notorious. There is other phenomena like the 150 kilometer echoes, which is some phenomena around the equatorial valley. And some other night electrojet, etc., etc. So this is what you would see at equatorial regions with radars too. So I will now talk a little bit about the practical applications of some derivations of the products when you have a radar that look in different beam directions. Each of those you calculate the line of sight velocities, and then you can combine all that, do some assumptions of the how the plasma is moving in that region, and you can infer how the plasma you can infer the whole three-dimensional plasma vectors of there, and also electric fields in that region that you're observing. And these again are plots in the x-axis time and the different components of the vectors. And you can see convection maps. You can see where the plasma is moving to the east, to the west, wherever you are like creating your geometry. This is an example of equatorial E cross B drift. So another interesting fact at equatorial regions is that while the incoherent scatter spectrum at any other latitude is like a double hump spectrum, when you point your radar exactly perpendicular to the magnetic field, the incoherent scatter spectrum gets very, very narrow, like very, very narrow. So it's very complicated with this technique to get the whole temperature ratio and the whole incoherent scatter theory needed to be revised, and it was revised in the 1999, I believe, starting with Salzer and Gonzalez, when like doing simulations to see how the spectrum looks like when you are pointing perpendicular to be. But what you can infer very, very accurately is the line of sight velocity, just because the spectrum is very narrow, so you're very sensitive to the Doppler shift. So you can have like a meter, 1 meter per second sort of resolution in the plasma to infer how the plasma is moving up and down. And the vertical drift here, you see on the lower part with very narrow error bars, and you can like determine very, very precisely what's that vertical drift. So that's a very nice application from radars pointing perpendicular to the magnetic field line. There are other observations and studies of polar car density structures that so this is a RTI from Riseren, which is right here in the cross, I believe. So it's very useful to study what's happening in the polar cap in the these density structures that cross the field of view of the radar. Also, study of gravity waves have been done with, for instance, with Pfizer. This is Negal 2018, where he does a study of up to 3 years, I believe, of how. So if you are measuring the whole volume and you have a couple of beams, like different beams, like characterizing the gravity waves that are crossing the field of view, you can have some information of the type of waves that are in the that are crossing the ionosphere in this case. So you can infer parameters like the intrinsic periods of the wave, the horizontal and vertical like wavelengths of those waves crossing the atmosphere, and direction of propagation of those waves. So what are the dynamics of on the coupling between the neutrals and the ionosphere, which is a very interesting study of that can be done with this data. So those are, and there are many other examples, but I wanted to go and all ask me to put emphasis on how can you access this data and what data is available to download, to plot, to analyze, and to use in your research. So different observatories have like maintain their own databases. For instance, with the AMISRs, we have a data.amisr.com database where you can see both Pfizer and Riceren. The Hicamarca Radio Observatory also has some link to go download the data. But we almost all the incoherent scatter radars publish their data in what is called the Madrigal database that you might be familiar with. But if you are not familiar with, the Madrigal database is a distributed database. So several institutions like maintain a database and they are ingesting that data that they post and they publish the data there, and then there is available to the whole community. And there is a central CEDAR Madrigal repository that is importing all the data from all these uh, instruments that or institutions that are hosting this database. So you can start always from the Madrigal database. I forgot to put there the link for that, but it shouldn't be complicated to find. It's the CEDAR Madrigal database for upper upper atmospheric research. And it doesn't only contain incoherent scatter radar, though it started with that, but it has like 22. This is a uh, this is a slide from Bill Rideout that used to be in charge, has been in charge from the Madrigal database, and this is one that there is an incoherent scatter summer school where it's available. Somebody is raising the hand, please. Yes, feel free to ask any questions. Ahmad, Ahmad, did you have a question? Do you have a question?
Yeah, we could have a question session later, Pablo, if you want to.
Sure, but just feel free to interrupt. So not incoherent scatter radars, but MST radars. What I was telling you before, in the case of equatorial aeronomy, you can get away with a very low powerful radar to observe coherent echoes. Like you will not get maybe incoherent scatter, but you could characterize like plasma bubbles and mesospheric echoes and equatorial electrojet. You can do with MST radars. It's like the mesosphere, stratosphere, troposphere sort of radars that are not very powerful. So there are meteor radars, Fabry-Perot interferometers, and so there are many types of also, of course, GPS, TEC measurements, and other instruments. So the Madrigal database is a very useful place to go and search for data. This also I took from Bill Rideout saying, where there are some rules of the road in every Madrigal, when PI is sharing their data, they put their contact there. So, and it's always a good like rule of the road to go and contact the PI and asking about the radar if for your specific application is. It doesn't mean that the PI would necessarily want to be a co-author or nothing, but you want to consult with the PI uh, to see if what you are using the data for is good, or or the PI will give you the best suggestions that there is to how to use the data and what kind of type of data. And so it's a great idea to consult with the PI list that they are listed in every Madrigal database. So there are several ways to access Madrigal. There is a web interface that you can access and really just select and click and download the data. But you can also install an API, and from Python, MATLAB, or IDL, you can create your routines and do a more systematic way of accessing data. And there is also, in the case of AMISR data, so there is, I'm sharing here a couple of links that will give you other links including, so the 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 Madrigal database has his own format is very common, and whatever radar is publishing its radar data in the Madrigal format, it will have you, if you learn that, then you can access to any published Madrigal radar data, and it will be the same. If of course each different radars have different flavors of it. For instance, there is radars that scan the atmosphere, so you will have information about azimuth and elevation changing. In the case of a miser, for instance, you will have like quasi-simultaneous measurement in all those beam directions. So all that azimuth and elevation, all there is a table, and you can access it the same way. But of course, there is also an AMISR format, and you can access access the data there and that AMISR format might have more information and more metadata that is not uploaded to Madrigal. But a very good start of getting data should be Madrigal. And then if you have more questions, and you can consult the PI, probably the PI will tell you, go and see the MISR format, which might have more metadata. There's a very useful tool, like a document that our colleague, Dr. Leslie Lamarche from SRI, also she created this MISR user manual that she mainly is the one that maintains it, but we have all tried to contribute a little bit with that. It's a very useful tool that you can documentation that you can go and see how to open, how to download, how to even plot some of the data that is in this type of radar. Also, in the same link here, you can see our operations. So this is the month of February. So just last month, how so a miser, I forgot to mention at the beginning, the poker flat, the Pfizer, has been operating almost continuously since it was started operations in roughly the end of 2006, by continuous since 2007, and has been collecting data 24/7 all year, all days of the year. And this is an example, for instance, a whole month of February, like all these incoherent scatter. And so when you access here, you can see, if you're interested, for instance, and I would love to know what was the ionosphere doing, and at a specific year, a specific month, a specific time, you can click here and you can go and get the access of the data over there. It will look something like that if you choose any of these. For instance, here it was this 2000, this giraffe badass. That giraffe badass was an experiment that was in conjunction with some rocket experiments at Poker Flat. So that there is a sort of a routine experiments. They launch rockets that go and measure in situ parameters in the ionosphere. So you click there, and the radar was giving support, and you can see how our usual mode, you will see something like an F region mode, like an E region mode, and resolve velocities. And you can click there in data files and get the data right there in the AMISR format, or you can go and click the access data from Madrigal, and you will get to the Madrigal data base, and you can obtain the data there also that way also. And you could see here some examples of plots, summary plots of each of these modes. The AMISR manual that I was talking about, that Leslie maintains, it creates like a very interesting like manual to how to deal with this the SRI, the AMISR format, but also I believe Lara Kamal helped, and probably Leslie, to create the Madrigal, how to also get some code and plots from the Madrigal database. So this is a very, it gives some a background, some explanation, and the common plots is a really great tool if you want to start digging into the data and just using Python code to 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 access the data and and to do these plots. So I really encourage you, if a student is, if the data is available there, get the data, just browse the data, check like what experiment, or try to see the difference between different experiments. Ask the PI. The PI is always happy to help and to explain what the differences of all these are. And yeah, that's all I have now. And thank you very much.
Wow, wow, wow. That's so great, Pablo. Thank you so much. That's a lot of information and very useful information for this gathering. And we appreciate you for taking your time to provide this information. Yeah, so the ground is open for questions. If you have any questions, you want to understand a little bit more, or you have specific questions, please feel free to answer. You can raise your hand or you can jump in, no problem.
I see in the audience some people that I know, and I also I see Leslie Lamar that I've been mentioning.
Yes,
That
Leslie Lamash is part of this.
And I also see Todd. Todd has been is and has been instrumental in the AMISR project since the beginning, and all of the. Yeah, there is a question.
Valence raised his hand. You may feel free to answer your question.
Okay, thank you, Pablo, and thank you, Jonah.
Mm.
Just I wanted to know more about how you can compute the TIDs using the ISR data. You explained that slide, but I didn't get the physics very well. Thank you.
Yes, yes, there is this study by Negal et al. So if you go and so this is the paper, and there is also his the dissertation is available to he did a study of using Pfizer data um, with four beams and doing so. First of all, it was like you have the electron density, but then you work with the perturbation. So so the delta electron density by the density, and then you apply some techniques to. I believe he used Scargill. The details are so I really suggest to go and read this paper. He explains in detail how he does it, but essentially is applying a spectral technique, so to obtain the uh, the 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 wave parameters, like so it's like a spectrum analysis of this and see what are the frequencies of these oscillations. And he does it for each of the beams. Then that he does cross correlation between the beams to know the wave, how, for instance, if you could do a cross correlation of two beams, and you will see the wave first hitting one of the beams and then the other one. So then if you that do like in three locations, he used four beams, and then you will be able to infer, for instance, how the wave was propagating. And you can do that as a function of not only time, but altitude also, because of the very powerful characteristic of an incoherent scatter radar that can resolve what's the ionosphere in as a function of altitude. And there is, of course, some assumptions also, and some about how the coupling between the neutrals and the plasma. Of course, it's like there is some. You have to be a little bit careful here, because what the radars are detecting is fluctuations in the electron density. Of course, and then which we have to so these are like the tracers. The electrons are the tracer. Wherever we have like a free electrons, those are the tracers for the radar to see. But this is the plasma, the ionosphere. There is like the the atmosphere, so the neutrals, what the neutrals are doing, and the gravity waves, of course, are like and the whatever the TIDs, those propagate in the neutrals. But then there is a whole theory of how, of course, what the radar is seeing is the ionosphere, so ionospheric disturbance that is propagating, and but it has so in this case, Negal um, like did that study for 3 years of Pfizer data, and determined that most of the waves are propagating in this and they are not propagating to the west. So there was a very interesting study about that. Uh, so I
Yeah.
really recommend you to go to this paper and his studies, how he did that.
Thank you, Pablo.
Yeah. So, Valence, can you introduce yourself a little bit to us, if you can?
My name is Valensa Biarimana from Mbarara University of Science and Technology in Uganda.
Okay. Yeah. Welcome,
Uh,
Valence. So,
I'm a lecturer in the Department of Physics.
nice. Excellent.
Medium.
Thank you. I think we have a question in the chat box, like spread F. I think spread F is not mostly in the high latitude. I think that is more in the equatorial region. Paulo, you want to say something about that?
Yeah. So when you so I showed here an example of what the incoherent scatter radar in the Hikamarka Observatory looks. Um, yeah, almost every night. Of course, there is a season of that. Uh, this is the spread of uh, how it looks like from the radar's perspective, and there are other examples, many examples. There are tons of studies with radars and the spread of which are like so, and there is many other studies on how the spread F initiates, because once there is spread F, first of all, yeah, you cannot measure incoherent scatter where this is contaminating the incoherent scatter, and also it disrupts other GPS. It also disrupts communications in several frequencies. So that's why there is a lot of interest on how to predict this, uh, how to characterize this, how to mitigate. But was there like a particular
It's
question?
about range and frequencies that are considered for spread-F analysis.
Oh, in computing the spread F, are both the range and frequency considered? Some light on
Yeah, I
that.
think the Ikamaka people can discuss more about that because their radar is more channel to do this analysis. I think the high latitude ones are not spread ever not common in high latitude regions.
Right.
So AMISRs, FISRs are not working useful
Y-
for that.
Yes, and so but it's interesting about the frequency because, for instance, Hikamarka is a 50 megahertz radar. So the wavelength is a 6 meter wavelength. And if you probe the same phenomenon with different frequencies, you will have different returns. And different frequencies will behave different for for different phenomena. And what but once the once the spread F is there, so imagine it's like some plasma bubbles like bubbling up, and then you have a lot of structure. So the radar studies are like you can see the shape of the spread F, and there are many like papers about the morphology, how lower spread F or like plumes, different types of plume of different uh, like different or number of plumes that come after it initiates. There is also very interesting scans from Altair radar in the middle of the Pacific in the so equatorial, where you that radar does scans, and you can scan from the west and see, and you can see how they are how they initiate at some point on the west, and then they travel to the east, and if the conditions are certain in above you, so you see how it initiates. But sometimes it has some initial stage on the west, and then it develops, and then it crosses your field of view. And this is also very interesting in this case because, for instance, Hikamarka is a radar that mostly is pointing up straight vertical with very little like some degrees, 2, 3, 4 degrees from vertical or from perpendicular to B. So what the Hikamarka radar is doing is looking up and is waiting at, and something will could cross the field of view, and then you will see. In the case of scan like dish radars, like Kwajalein, for instance, in the middle of the Pacific, you do a scan from the west to the east. And I forgot also at Hikamarka, there is a mini AMISR, like 16 or 14 panels, I believe, that there are studies by Fabiano Rodriguez and maybe Jose Maria Gomez too, that they scan. So with an AMISR system, you can scan from west to east, and they have also done studies of spread F in 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 uh in the whole field. So in a larger field of view, that Hikamarka just looks perpendicular, sorry, just vertical position, and see what's happening crossing. There was, I believe, this is Claudia from Brazil. Note that spread F is a generic term for plasma irregularities equatorial region. That's correct. Range and frequency spread F of types. Right. The ionoson. That's where the term comes from, spread F, because and rather like a ionogram, like a clear ionogram, when spread F happens, you see how that line spreads, and the term, I believe, comes from that. But of course, the phenomenon is the plasma bubbles, like a low density that you can imagine at equatorial regions, the the magnetic field lines are parallel to the ground. So, and plasmas like to stay around the magnetic field lines. Imagine the electrons, the ions are are sort of trapped along magnetic field lines. But then there is like all of a sudden there is a pressure of low plasma that like it passes a threshold and then it creates a disturbance and it's like then it starts bubbling up, let's say. But it's the fact that the equatorial regions, the magnetic field lines are parallel. They are good to it's like a pressure like a, like some low density plasma is trapped and then all of a sudden disrupt and there is like this phenomena that plasma bubbles start coming up. So that doesn't happen at, at higher latitudes where the magnetic field lines are like a diagonal or vertical to the ground where the diffusion of the plasma is along the magnetic field lines allows it to for the plasma to distribute easier. But at equatorial regions, it's like it builds like a pressure, and all of a sudden, certain conditions happen, and then there is this disruption, and the plasma bubbles happen. Yeah, it's a very interesting phenomenon.
Yeah. Thank you, Dr. Reyes. This is wonderful. Can you introduce yourself, Miss Bruno? You, sorry, I would like people to introduce themselves. I think we are in that section now where we can get to meet people. So if you want to introduce yourself, please take the floor, Mr. Bruno.
Yes, good evening, Doctor.
Yes.
My name is Bruno. I am a land surveyor by training,
Oh,
but
great.
crossing towards ionosphere studies for my master's and hopefully the PhD. So I'm glad to be part of this. I am currently working with Chambogo University and helping out on satellite geodesy and geodetic astronomy. Thank you.
All right. Yeah, good to have you here. You are part of the people that we want to see their perspective regarding ground-based instrument over Africa and how best we can have you participate in this forum. So thank you for coming, Mr. Bruno. I think we have another question from Dr. Emmanuel. Um, Do you have time for question? Yeah, we can. Dr. Paulo, do you want to take that question?
I believe it's just like
Okay,
giving
comment.
a comment, which
Okay.
yes, is very interesting. I haven't seen that study. I would love to see. It's been a while that I don't see spread F since I used to work at Hicamarca since year 2000 to 2005. I saw a lot of that, and also I did my master's and PhD with Professor Erhan Kudeki at the University of Illinois, and I keep studying about equatorial ionosphere. So I see we even did a campaign, a rocket campaign in Quadraline to study about the initiation of spread F. But since I started working at SRI, it was more about the upper latitudes. There was no spread F there.
Yeah.
But yeah, I did some interesting spread F studies before.
Yeah, so this is thank you very much, Pablo. Uh we have people joining us for the first time because I started earlier when some people are not here. Like we have 15 people that joined this month of March. And if you are here, you want to introduce yourself, we have like 2-3 minutes to do that if you want to. Your name is listed here. You want to introduce yourself, tell us the country you are joining us from, what you are doing in your research. Yeah, so that particularly people that are around that equatorial region of Africa where we are, okay, David is raising his hand. Please go ahead, David.
Hello, everyone. It could be good morning, good evening, wherever you are. My name is David Molindwa. Also come from Uganda.
Okay.
But right now I'm stationed here at Warsaw University of Technology. I'm carrying out some research in a different area of mobile mapping. But back home, I'm one of the owners of the GNSS ground antennas. But I would really have much interest in this area, given that most of Africa is not really well explored. So it would be really of my interest to really jump into this.
Excellent.
Yeah, and I'm glad to be here.
Thank you. Do we have Jeffrey here? Babagot. He's from, I'm interested because he's from DRC. I want to meet people around across the region. If you are here, you can just introduce yourself. We have someone from Ethiopia, a lot of people from Nigeria. Yeah, please feel free to jump in and introduce yourself. And so that's, given that we have a little bit of few people here in this meeting, it's a series of meeting that is channeled to building a network of people that can work together. So by that, we have a mission in mind to put ground-based instruments over the equatorial region of Africa because of the interesting aspect in physics. So you know how space physics meets equatorial region. There are a lot of dynamics that goes on there, and due to lack of instrumentation over this region in Africa, it has been set aside in the scheme of things. So this is a kind of way to bring researchers, students, scientists together, lecturers together to talk about how we can make this possible. And we also teach, we train in development, such kind of presentation, wonderful presentation that was given by Dr. Reyes today is a powerful way to educate people and get them on board. By the time we have those instruments, it could function much more better. We are also interested in data distribution, like Dr. Pablo said. You can, it shows to you how well you can access the data. And thank you so much for doing that aspect because a lot of people want to access data, but they couldn't know how to do that. And I will ask for permission from Dr. Paulo Reyes if we could share your presentation so that people could have access to the link to access those fantastic uh,
Yeah,
uh,
definitely.
materials. Yeah, thank you. Thank you for that. I think we have Dr. Emmanuel raising his hand before I move to the next thing here. Please go ahead, Dr. Emmanuel.
Good afternoon. I don't know if you can hear me.
Yes, we can.
Yeah, good afternoon. I'm Emmanuel Laguju.
Okay.
Uh, 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 my background generally is earth physics for my master's, then my PhD.
Oh, Libya. Oh, Liberia. Okay. We can hardly hear you, Dr. Emmanuel. Sorry.
Is in space physics.
Okay. We can
So
hear
I'm
you.
from mostly coming from atmospheric phenomenon such as atmospheric gravity wave.
Oh, okay.
How atmospheric gravity wave can actually influence the
Okay. Yeah, it's very, yeah. Sorry, Dr. Emmanuel, we can hardly hear you. Well, thank you for introducing yourself. And we have Mr. Sampson. Do you want to go ahead before we go to Naomi?
Thank you, Olu
Hello, can you
Juna.
hear me?
Uh,
Hello.
Hello, everyone. I'm Yuombi Irie Samson. I'm a civil engineer, especially a geodesy analyst. I work in Côte d'Ivoire, Ivory Coast, like a geodesy analyst, and I work in the National Geodesic Center Côte d'Ivoire. So I'm very happy to follow for the first time this CONGA meeting. Thank you.
Yeah, welcome. Thank you for showing up and showing interest. We invite you to join our next meeting as well. So as I think I have you in the email list, so I can send you the consequence emails. Miss Naomi, do you want to jump in?
Okay, thank you so much.
Mm.
Good day, everyone. My name is Nahum Maundu. I'm from Pan University. I am a Master of Science in Physics student in final year, and I'm working on irregularities and their impacts in the low latitude region. I'm glad to be here. Thank you.
Yeah, I couldn't, it's difficult to hear you. Are you from, which part of the country are you from?
From Kenya.
Kenya. Oh, okay. Nice to have you here. It's very hard to hear you, but it was good to have you here, Miss Naomi.
Yes.
Yeah. So we have somebody here with the number. If you want to go ahead, it's always good to have your name instead of the number. But you can please go ahead.
Okay, good afternoon, everyone. I hope you can hear me.
Yes.
Okay, thank you for this wonderful presentation. I am by name Ahmad Khalid, a geophysicist by profession, and also hoping to join my MSc in planetary sciences very soon. I'm very glad to be here and be part of this journey. Thank you all.
Excellent. Where are you from?
From Nigeria.
Oh, from Nigeria.
From Nigeria.
The North Nigerian? Or
Yes, northern part of Nigeria.
oh, great. Thank you. Thank you very much.
Thank you.
Yes.
Thank you.
And yeah, thank you all for introducing yourself. That's wonderful. And lastly, I just want to show us very quickly that we have a number of presentation coming up, very interesting from very wonderful people that will be giving us different aspects of what they are working on. Today was Dr. Pablo Reyes, and he's my very wonderful colleague, and we work together most of the time. And thank you, Dr. Paolo, for agreeing to talk to us today. And next month, we're privileged to have Dr. Kit Groft. Everybody knows Dr. Kit Groft from Boston College. He has a lot of interest in Africa, and he has shown that by so many ways, in so many ways. I remember together with the late Dr. Duarte, and they work together to put so many instruments over Africa. So next month he will be talking to us on so many things that he has been doing as well on instrumentation. And after that, the coming month, May, we will still have a wonderful, well-experienced person, Dr. Valadari Sesa. He has been working on instrumentation for several years, maybe before I was born. So you know how interesting that will be. So we have a lot of interesting outlines. We also have Dr. Jose Maria Gomez with Dr. Fabian Rodriguez. So they are going to be telling us what they are doing on the SimPy, how SimPy is efficient, and so many things they have been doing on this wonderful low-cost receiver. So as you can see, we have a lot of uh, lineup of speakers for 2025. So up to August, we still have very good people that will be talking to us. So I advise you not to miss any of this. And yeah, so lastly, we have this YouTube channel, but it's not public, it's private. And what we do, because we have this video every time and it takes a lot of space, so we try to put them in the storage. So this serves as a storage for us. So if you are interested, some of the time when I send email out, if you look at under it, you will see the link to the YouTube channel. So once this video is completed, we are going to send it to the YouTube channel. So any one of the video you miss or anything, you can always access it from there. I think I have somebody raising up his hand. I think that will be the last person who will be taking today. Sorry for taking your time. We are a little bit over time, 10 minutes over time, but we can afford more 5 minutes, right? So if Mr. Adamu Bella could take the floor.
Good afternoon, or good evening, or good morning, everyone. I am Adamu Bala. I'm in Nigeria. I work with Modular University Zaria in northern Nigeria as a lecturer. And presently, I'm also doing my PhD in China. Thank you. This is my first meeting time attending the meeting.
Excellent. Excellent. Thank you, Mr. Adamu. Thank you for attending this. And I appreciate everybody that have been here patiently. And this is just what we want to do, to get to know people, form a network of people that can work together, try to make data available, to people, and so that they can do their research and do their publications. So I remember sometimes ago I was discussing with Dr. Paolo, and he was mentioning his intention to build a radar in Africa, Incoherent scatter radar in Africa. So yeah, this is a good platform that could encourage such an idea. So always come and join us, Dr. Pablo, even though you are here for the talk today, we invite you all the time to join us. So is there any other question that or any comments? All right. So thank you all for today's meeting. It's has come to the end. I don't think we have any question in the.
Sorry, I have a question.
Okay, go ahead.
I have a question. Yes, before the next meeting, we will have any other updates before the next meeting, regular updates or
Yes,
information.
exactly. So we have your email. So if there is any update, to email you the updates.
Okay. So I want to take this opportunity to really appreciate you and Dr. Pablo and you yourself. Thank you very much for giving us this opportunity. And we hope that in the nearest future, we'll do what we can do to explore the Earth's ionosphere in a very good way.
Yeah.
Thank you.
Thank you, Mr. Dr. Emmanuel. Are you from Liberia?
I work in Liberia. I work with William V. Sportsman University in
Okay.
Liberia.
Yeah.
But I'm more like a Pan-Africanist, so I'm everywhere.
All right, sounds good. So I always want to know where people are from, so that when we are ready to deploy instruments, we will know who to call on a specific country. So thank you so much.
Yes, exactly. Yes, because currently we don't have any sort of such instrument in Liberia. So I would really like to host one of the instruments.
Excellent, excellent. Good to know that. All right. Thank you, guys. Thank you so much, everybody. And this is the end of today's meeting. Thank you. Thank you, Dr. Paulo. Thank you again. Thank you so much.
Thank you. Thank you.
Mm-hmm.